During the last 3 lectures or so, we have been discussing about competing theories, namely quantum mechanics and hidden variables, and we talked about the objections that Einstein and co-workers they had, which is known as Einstein, Podolsky and Rosen paradox. Then we introduced certain inequalities originally due to John Bell, and there are many variants thereof, which provided a conclusive test for quantum mechanics over the competing theory of hidden variables. What we will do now is to discuss a possible applications of the principles of quantum computing to what we will call as the cryptography. Now, what is cryptography? So, cryptography is basically the subject of encoding a message, which we will call as a plain text, to a code which will be called as the cipher, and send this coded message to a receiver over a public channel. By public channel, I mean it could be a fiber optic channel, for instance, but basically a channel which is open for any outsiders, and in principle it should be possible for somebody to eavesdrop on your conversation. Of course, the conversation does not really mean oral conversation in this case. It means a coded message is being sent over the internet and to a receiver. Now, at the other end, when a receiver receives it, since the message was coded, he will need to decode it and finally convert the cipher text back into the message in the form in which it was sent. So, this is the principle of cryptography. So, let us look at what are the elements of cryptography. What do we want from the subject of cryptography? So, there are 4 or 5 challenging things about cryptography. So, first is privacy. That is, whatever you are sending should not be understandable by anyone other than the recipient. Now, what I mean by it is very simple. You see, when 2 people who are not familiar with a third language, for instance, if you do not understand French, you and your friend, they understand only English, then even if you happen to hear a conversation which is going on in French, it would not mean anything to you. So, in other words, there is a privacy element in the conversation. So, it should be understandable to the person for whom it was meant. The second thing about the secrecy is that this secrecy should not be taken too far. Most messages have a lifetime. What I mean by that is this, that supposing you are doing a banking transaction on the internet, during the time it takes for you to send the message to your bank, let us say to transfer a certain amount of money to another account, and the bank executes that transaction, the text remains confidential. So, therefore, after that somebody cannot tamper with that message. For instance, you cannot send 500 rupees to somebody, and somebody cannot alter that message and say send 5,000 rupees instead. So, there is a duration for which the secrecy, need for secrecy may be valid. The second point is data integrity, and this is a very important point, that it should not be corrupted during the passage over a public channel, and this is of course a very big problem. There are noises in the channel, but even if you assume there are no stray noises in the channel, you do not want a third person whom we will call eavesdropper to be listening into the conversation. I have already explained, I mean use the word listen in a general context of tapping the conversation. The third point is what we will call as a non-repudiation. Supposing you have sent a message and later neither you should be in a position to say or decline that you had sent that message, nor the receiver should be in a position to say that he did not receive that message. So this is the element which we will call as the non-repudiation. And finally, the authentication. The authentication works like this. The sender, again let me come back to the example of you talking to your bank. Now the bank should be in some way certain that the instruction that is given to it is being given by its client, that is you. And that is how the banks use various types of protection, the simplest one being use of a password. It could be one-time passwords, so many other things that you could be familiar with. So authentication of the sender and the receiver, these are very useful elements of cryptography. Incidentally, cryptography as a subject has a very long history. In fact, the earliest known cryptographic protocol was used by Julius Caesar, and Julius Caesar used to send cryptic messages to his soldiers in their fight against the Gauls. And of course that was a very trivial cryptography. What he used to do is to advance every letter by 3. For example, the letter A would become D, letter B would become E, and so on and so forth. Coming back to not exactly modern era, but Queen Elizabeth I had established a section of espionage, and where it dealt with creating and breaking a code. Then we make a big jump on time. During the World War II, Germans used an electromechanical machine known as Enigma for sending messages to its troops. In fact, breaking of the Enigma code had a great deal of influence on the result of the Second World War, particularly in the naval battles. So let us look at what is a secured communication. Is there any communication which in principle is secured? Now it turns out that most of the codes may be given, may be broken given enough time. A code which is known to be robust, it is called Onetime Pad, or it also goes by the name of Vernam cipher. Now let me explain the principle of this Onetime Pad. So Onetime Pad could be a code which is agreed between two friends to be used once and once only. Now for instance, if you decide that I will send a written message, and in that written message every word will be picked up, let us say from a particular dictionary, say Oxford English Dictionary. Now what I do is this, I pick up a word, find out on which page this word appears, which column, which line. So I will, instead of that word which I want to send, I will code it by page number, column number, line number. Now my friend who should be in the possession of an identical copy of the dictionary, all that he needs to do is to look up that what is this code, what does this code translate to. So in the way he can find out, and this could be any other book as well, it does not have to be restricted to a dictionary. The advantage of such a code is that if you use it once and once only, it can never be broken, because if you repeat, there is a possibility of people trying to find out what is this document that you are using or relying on for sending a code. So basically the way I would describe it is this, that suppose I have a random sequence of binary digits which will be used as codes for messages, and I will be using it once and once only. So what happens here is this, look at this line here, So, this is the code that I want to send 1001, 1101, 1010, 1101. This may stand for some letters or whatever you have, but this is the plain text, that is why P, that is what I want to send. The plain text is the name given to the message that you want to actually send. Now what I do is, I generate a random key. This random key is basically a sequence of random binary digits which the sender has and an identical copy of it the receiver has, no matter how far the receiver is located. Now what happens is this, that the cipher code is simply addition modulo 2 of P and K. You can see this here, 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0. So this is the plain text, this is the key of which both sender and the receiver have a copy, and this is C, that is the coded or the cipher message which is sent over a public channel. So basically every sequence Ci is obtained by addition modulo 2 of Pi with Ki, and I can recover the Pi back at the receiver's end by writing Pi is equal to Ci addition modulo 2 of Ki. Now as long as this Ki is used once and once only, no one can ever break this. So this is a one-time pad. Now the point is this, how do you generate one-time pad? We will be discussing today on the existing ways in which the one-time pads are generated. Now this obviously cannot be an agreement between two friends that I will be using an Oxford English dictionary or some novel that each one of us have taken fancy to. So this is the existing code which is being used extensively both in military communication and financial transaction, is known as RSA crypto system. RSA, which was invented by three scientists in MIT in 1977 named Rivest, Shamir and Adelman. They use what is called as a public key encryption for encoding and sending data over the internet. Now it enables one to establish the identity of the sender and the receiver, and the data remains absolutely confidential. And let me explain how it works. So what RSA uses is what is known as a trapdoor function. A trapdoor, as you know, is a door which opens one way but is difficult to open the other way. One of the most common examples of a trapdoor function is the valve that exists in our heart between the auricle and the ventricle. It is a one-way valve which allows the blood to flow only in one direction, so that the blood does not flow back from ventricle onto the auricles. It is a trapdoor function, one-way valve. So in mathematical language, I would call a function as a trapdoor function where f is an easy problem. In the language of computer science, an easy problem is one which can be computed in polynomial time. We have seen this and discussed it several times. But however, its inverse, that is coming back from that trapdoor to the other side, is a hard problem, usually a non-polynomial time or an exponential problem. Now, what RSA does is to choose the following as examples of the trapdoor function that we use. The easy problem is multiplying two large primes. So, multiplication of two large primes is my one way function. This is multiplication, as we all know, is an easy problem. But given the result of multiplication, the inverse problem, so this is my f. The inverse problem is, given the result of multiplication, to find out the factors, prime factors. We have discussed this in detail when we were talking about source algorithm, and we had pointed this out as one of the possible successes of the quantum computers whenever it comes into being, that there are now quantum algorithms which probably make it possible for computing what are known as integer factorization. But we are discussing still the classical regime where f is easy, multiplication is easy, factorization is difficult. Just to go back to our school days, we used to use what is known as the Euclid algorithm for calculation of factors. As you know, what we used to do in Euclid algorithm is to try to do repeated division. Now, so what we do basically is this: start with whether the number is divisible by 2, number 3, 4, etc., etc. And of course, you could reduce it, because if it is divisible by 2, you need not check, go further. But basically, it requires of the order of square root of n attempts before you have found a factor, if there is any. The reason is that if a number is known to have 2 factors, then one of the factors has to be less than or equal to the square root of n, and the other factor, of course, is greater than or equal to the square root of n. Now, but as we know, square root of n is a hard problem. Now, we will now be talking about the RSA algorithm, but before we can discuss what are the elements of RSA algorithm, I need 3 major components, and these 3 major components are the following. So, the first one, if I can look at the slide, is what is known as the Formas little theorem, not to be confused with the more famous Formas last theorem regarding existence of things parallel to Pythagoras theorem for other integers. This is a different theorem, much used in discrete mathematics, but not as well known. Now, basically what we are trying to say is this, that supposing I have a prime number p, and consider any number a belonging to the set of integers z. Now, the number a is such that a is not divisible by p. So, in other words, a is not equal to 0 mod p. In that case, the Fermat's little theorem states that a to the power p minus 1 is equal to 1 mod p. So, this is Fermat's little theorem. let me give you a quick proof of this. Now first consider a set of numbers 1, 2, 3, 4 like this up to p minus 1. Remember, p is a prime number, so there are no factors. Now having done that, suppose I take any element out of this set. Let me choose an element small s belonging to S and another element R also belonging to S. Now suppose I multiply both S and R with A. So I get AR and AS. Now under what condition is AR equal to AS? Of course everything is mod P. Now you can bring this to that side and you can immediately say this means A into R minus S equal to 0 mod P. But we have already started by saying A is not divisible by P. So if A is not divisible by P, it means R minus S are divisible by P. So R and S are divisible by P. But we have already said I didn't mean R and S, I said R minus S is divisible by P. Okay. But we have already said that R and S are less than P. So therefore, this statement has no solution, unless of course R happens to be equal to S. So therefore, if you multiply each of these members of this set S by a number A which is not divisible by P, then AR equal to AS mod P implies that R is equal to S. So what am I doing is this: when I multiply each of these numbers by A modulo P, I am generating the same sequence of number in a different order, because no two numbers can be identical is what we have proved, that if you have AR equal to AS, then it means R must be equal to S. So therefore, the set S and the set that I obtain by multiplying each element with A. So original set is 1, 2, 3, 4 up to P minus 1, and the set S prime is obtained by multiplying each number with A. So I have got A, 2A, 3A, etc. A times P minus 1. So these two sets are identical sets. Mind you, I am talking about modulo P. They are identical set, but arranged in a different order. So let us look at this. So what we are saying is this, that if I do this, then I get the same set. Supposing I now multiply them throughout. So I get 1 into 2 into 3 up to P minus 1 is equal to, there are P minus 1 terms. So A appears P minus 1 times. So I get A to the power P minus 1 into 1 into 2 into 3 up to P minus 1, though in the second set they would appear in a different order. So comparing the two sides, I get A to the power P minus 1 is equal to 1 mod P. So this is Formas' little theorem. The second theorem or element of proof that I require goes by the name of Euler's theorem. The same Euler whose algorithm we wanted to use for factorizing but were not successful. But before I do that, let me define what is known as Euler's tocent function. It is shown in the slide. So, Euler's tocent function corresponding to a number n, integer n, is the number of integers which are less than n, which have no common factors with n. I will illustrate what I mean by an example. Now, when we say two numbers have no common factors, one also uses a phrase that these two numbers are co-prime. Remember, we are not talking about two numbers being primes. We are simply saying that two numbers are co-prime. It means there is no common factor between them. For example, a number 15 and a number, let us say 16, they are co-prime to each other, because 15 has only factors 3 and 5, and the only factors of 16 are 2. So, therefore, there are no factors. This tocent function is essentially if you count the number of integers less than n which do not have a common factor with the argument of 5. Just to give you example, consider phi 18. So, phi 18 is equal to 6. All that I do is to count how many numbers less than 18 have no factors common with 18, and we use 1 as a part of the set by definition, 2 is a factor of 18, 3 is, 4 is, I mean it is not a factor, but there are common factors between them. 5 does not have a factor, 7 does not have a factor, 11 does not have a factor, 13 and 17. Clearly, if n is a prime, then phi of n must be equal to n minus 1, because all numbers below n are co-prime with n. In the next lecture, we will continue this discussion and try to come up with what the RSA algorithm is all about.